Hello, my name is Rafał Leszko, and my talk is titled 5 Levels of High Availability from Multi-Instance to Hybrid Cloud. In this talk, I would like to tell you about high availability levels and focus especially how different availability levels affect your system architecture. But first, a few words about myself. So I'm a cloud software engineer at Hazelcast. Before I worked at Google and CERN, I'm also an author of the book Continuous Delivery with Docker and Jenkins. And from time to time, I do conference speaking and some trainings. But as a daily job, I'm a software engineer. I live in Krakow in Poland. Also, a few words about Hazelcast. So Hazelcast is a distributed company, and it's distributed in two meanings. First is distributed because we produce distributed software. We have 3 products. The most widely known Hazelcast IMDG, which is Hazelcast in-memory data grid, which is an in-memory data store used in many cases for caching. Second product is Hazelcast Jet, which is a library for stream processing. And the third product is Hazelcast as a service, which is Hazelcast Cloud. But we are also a distributed company in a second meaning. And the second meaning is that we all work remotely. So we have engineers all over the world. So the contact between our colleagues is also distributed. Our agenda for today is pretty simple. So there will be a very short introduction about high availability in general, and then we will walk through all high availability levels that you can use in your system. When I'll be talking, I would like you to focus on 2 things. The first thing is, which of this level is the level that you use in your software? I guess you use some high availability levels, so this list is complete, so you may place yourself in one of these levels. And the second question I would like you to ask yourself is, would it be easy for my current architecture to level up, to go to a higher level? And with this question, I recommend this question for listening to the rest of this talk. So let's start with the introduction. So currently in every system, currently in the center, there is a service. Like we sometimes call them microservices. Sometimes we call them microservices, even though they are actually macroservices. But it doesn't really matter. It doesn't matter if it's macroservice, or even a serverless lambda. What matters is that a service is stateless. And it's stateless means that we can replicate it and put it wherever we want. So if a service contains just business logic, no dependencies, then what's the problem? Just imagine the world when we have just services with no dependencies, like the calculator services everywhere. It would be super easy to develop. You can deploy it on your computer, in the cloud, wherever you want. It works exactly the same. However, it's not how the IT world looks like, because like in real life, each service has some dependencies. It can be a dependency to a database or some queue or some other service, something that has some state. And that is the problem of the high availability. So the data is the problem in the context of high availability. That is why in this talk, I will focus mainly on the data part or on the state part, and less on services. I will always show the whole architecture. However, I will focus, the main problems will be with the data. And as an example, I will give it with the Hazelcast, which is an in-memory database. So let's start with the not level 1, but level 0, which is deploying everything on one single instance. The diagram for this looks as follows. So we deploy everything like, let's say on our laptop, there is a request going to our system. It goes to the application service and the application connects to some database, which is located on the same machine. So you may think like, why do I even show it? Because it's like, what crazy developer would put everything on their machine? But remember that not every system has to be highly available. Like for example, like an idempotent batch job that you can always repeat. It can be placed, executed on one machine, and it's perfectly fine. I did a latency experiment running Hazelcast on one machine with some service and checked the latency. And the result was I measured like read write, and it was like 80 milliseconds per 10,000 entries. So this does not tell us a lot. However, we will compare it later to other highly available levels. But you can already tell that this latency is very low. It's, you know, it's much less than millisecond per query. So it's good. So what does level 0 mean to you? So single instance means obviously no high availability, no scalability, but from the good side, and why you could consider using this for some use cases, latency is very low and the data is very consistent. And remember, data consistency is something like a strong data consistency is something that we lose when we with the higher levels. You will see it. So let's go straight to the level 1 multi-instance. So multi-instance means we run our software on multiple machines. So if one machine is down, the system is still available. That is the requirement. Architecture for this looks as follows. So request goes to the load balancer, then we go to the application services which are located on multiple machines, and then the application uses some stateful thing like a database, which is also located on multiple machines. So on this diagram, the only thing that is single is load balancer. However, we will not focus on load balancer because these problems are usually well solved. You can use some DNS-based load balancer or just something from the cloud, which is very reliable. So we will not focus on load balancing part. We'll also not focus on the application services because, as I mentioned in the introduction, this is the easy peasy part. No problem with the services. So we will focus on the data. So, and in our level, the assumptions are that both machines are running in a local network, which is fast and reliable. As an example, you could run 2 EC2 instances in one local network in the same region. So this is how it looks like in real life. So it's usually like these 2 machines in local network are usually in some racks in the data center. This image, by the way, is taken in Geneva and CERN. And by the way, if you happen to be in Geneva, you can visit CERN, not only their data centers, but also all these colliders, all this physics. So you can visit this for free. So it's very interesting. If you happen to be there, I really recommend go to the tour visit to CERN. So coming back to our example, so we have 2 machines with 2 databases, and now we have to solve a problem of the data replication. So this will be like what I will describe now is like a little history of the data replication. So how people tend to do it, how it's done now. So in most like SQL databases, when it all began, usually the approach was to use active passive replication or master slave. So application services, they accessed only one database. However, all the changes were replicated to some second instance, which was passive, which was not used. This passive instance, it could be also master slave. So the second machine could be also read only. But the important thing is that we are writing only to one database instance. Now, if this database fails, then application services, they do a failover to the second instance, and it all works correctly. So this is like, you know, it is a classic approach with most relational databases. You can still connect it with the, combine it with the sharding for the performance, etc. So you can do something more here, but that is the basic idea. Now with the emerge of NoSQL databases, the idea was that, you know, it's not good enough for us, this master slave, even with the sharding, it's just performance is not good enough. So there was an idea of the clustering. So clustering means that now application services, they are connected to all instances of the database, and each of the instance store part of the data. So now but it's not only store part of the data, but also backups of the other partitions. So if one of them crashes, we still can migrate the data and restore and not backup partitions, and not have any data loss. Like, to give you an example how it works in Hazelcast, to go slightly deeper. So Hazelcast is like a key value database. Now we partition all the keys, and each member stored some of the partitions. Like the member 1 stores partition 1, 4, and 7. Now the backup of these partitions are stored on some other members. And the rule is that the backup of the partition is always stored on another member. So the partition 1 backup is stored on member 2, the partition 5 backup is stored, the partition 4 backup is stored on member 3, and the partition 7 backup is stored on member 2. And now, if member 1 crashes, then we restore the backup partition and we don't experience any data loss, even though Hazelcast is, remember, in-memory database. But still, losing data is not a good thing. So, and this is basically the whole idea how the clustering looks like in all this, like all NoSQL databases. So now the question is like, should this replication be synchronous or asynchronous? And so the question is like, and also for active passive replication and for clustering, should it be synchronous, which means that we favor consistency, like strict consistency, or should it be asynchronous, which means that we favor the latency, because we then don't need to do a synchronous backup, which is obviously faster. And before I answer this question, I did a second latency experiment. And now I run like Hazelcast on 4 machines, and each machine contained one Hazelcast instance. They all formed a cluster, and I measured the latency for the scenario when the backups were written synchronously, which means that there was a strong consistency of the data. And this is the result. So the latency was 3000 milliseconds per 10,000 entries. It looks very high comparing to the single instance. However, in reality, this is still an acceptable latency in most of the cases. That is why, by default, in Hazelcast and in most NoSQL databases, the replication is synchronous, because there is a big, this is like a really easier to think about the system when you know that your data is inconsistent state. Now, is it the same? Obviously, you can configure this if you want. Is it the same for SQL databases for master-slave replication? That will depend. Like MySQL, for example, they do asynchronous replication by default, because like this, the mentality of this relational databases is that, okay, failovers are very rare, so it should not happen, and the replication is very costly. That is why probably by default you have the asynchronous, but as in most databases, you can configure this. Short summary. So what is level 1, putting your software on multiple instances, what does it mean to you? It means that in most cases, you can still have data consistency. Most tools support it, which is very good. You can use some cloud-specific toolkit like AWS SQS supported. And this setup is very simple, even for on-premises. If you would like to set up Hazelcast, it's just, you don't have to do anything. It just members find themselves, form the cluster. So really setup is super simple. From the downsides, like if you would like to have low latency from multiple regions, then obviously it's not possible because you are located still in one region with your software. Level 2, multi-zone. So multi-zone means that if one availability zone is down, the system is still available. So availability zone consists usually of a few data centers. This is an availability zone, a data center from Facebook. The idea of data center, of availability zone, is that it has a dedicated power supply, it has dedicated all the infrastructure, because you don't want the other availability zone to be affected by any external factors. So that is the idea of availability center. And our system looks like this. Again, the request goes to load balancer, and load balancer forwards the traffic to application services. They use databases, but now application services are located on the instance, on the machines located in the different availability zones, and the same with the database. So you may look at this diagram and say, like, you know, it looks pretty similar to the diagram from multi-instance. So is multi-zone deployment any different than deploying to multiple instances? And I would say it's not much different, but there are some differences. So maybe let's first start with why it isn't that much different. So I did again like the latency experiment and measured the same thing like now, but now I had like Hazelcast instances in multiple zones and measured the latency of read writes, and that was the result. So obviously the latency is a little higher, but it's not much higher. It's not even twice higher. It's still under 1 millisecond per entry, which is usually acceptable for a synchronous communication. So in this sense, it's not much different. And you know, the latency is not that much different because this availability zone, they have dedicated infrastructure, dedicated networking cables between each other. So they don't use public infrastructure. That's why it's not way, and they are not far away from each other, availability zones. So that is why this result is comparable. But I also say that there is some difference between multi-instance and multi-zone. So now let me explain what is the difference. So that is a sample deployment of our database. So the assumption here is like we have machines at least 2 availability zones. There is a fast and reliable networking. For example, we can have EC2 instances in 2 AWS availability zones. Now, let's move, just remind ourselves like what I described with the Hazelcast. So you remember there were partitions. The rule was that backup of the partition needs to be stored on a different Hazelcast member. But it can happen that we may end up with the situation like this. So we have 4 machines in total, 2 machines in zone 1, 2 machines in zone 2. And now there is a partition which is stored, let's say partition 1, which is stored on member 1 on machine 2, and the backup of the partition is on member 2. However, the member 2 is located in the same availability zone. So if one availability zone is down, we lose the data. So that is definitely not something we wanted. And we thought how to solve it in Hazelcast, and we came up with the idea of a feature called zone aware. So the Hazelcast itself is aware of the zones and in which zone it is located. This is a little tricky. It looks very simple. Actually, the configuration for this is very simple, but to implement it was a little tricky because availability zone is a concept of the cloud provider. So it is different. To check availability zone is different on AWS, on GCP, on Azure, on Kubernetes, or it can be different everywhere. That is why we came up with the idea of the plugins. And you just use the plugin, and then plugin uses the API of the given cloud provider or the given environment, and it checks, okay, in which availability zone I am located. And then each Hazelcast node is aware of the fact which is my availability zone. And then as a cluster, they can decide that, okay, I will never put the backup in the same availability zone, because in case of the zone failure, I don't want to experience any data loss. That is why I said no, but yes. So generally, the deployment for multi-zone is the same as multi-instance, but please make sure that your data store or whatever your state keeping thing in your system is zone aware. Because like it's, don't take it for granted. It's like, even from cloud portfolio, you will find toolkit that is not zone aware. Short summary. So level 2 multi-zone, what does it mean to you? I would say it's currently like top 1 choice, because like you can still have data consistency and you are very highly available with your system. And most cloud-specific toolkit supported, which is very good. From the downsides, you have to make sure that your tool supports it. And also the same with the multi-instance. If you build your system worldwide, then I mean you cannot build worldwide. You are located in one geo region. Then the latency from other regions is obviously high. That is what we will change with the next level, which is multi-region. So multi-region, we go globally. Now our system will be global. The rule here is if one region is down, the system is still available. And the diagram for this looks like this. So this time we'll need some geo-load balancer so that your traffic is forwarded to the closest data center, closest in terms of geographic location. Then in each data center, you will have another load balancer, which load balances the traffic to your application services. And they use the data store, which is located in the same data center, and between data centers, there need to be some synchronization, which is called geo-replication. So the assumption here is like, the problem here we will have to solve is how to replicate the data between regions. And the assumption here is we have machine in at least 2 geographical regions, and the network between them may be slow and unreliable. Now, if you think about it, what's the deal with multi-region? I mean, what's the problem with the multiple locations? And actually, like, the root cause of the problem is that these data centers, these regions are far from each other. Like if you take Finland, for example, and Oregon and GCP, the regions, it's like physically, it's 10,000 kilometers. So even if we do a simple math, like 10,000 kilometers, the speed of light is 300,000 kilometers per second, the distance is 10,000 kilometers. So with the calculation, we have that round trip time of a single light is 60 milliseconds, which is a lot. And it's like the speed of light, it was in the vacuum. In the fiber, it would be at least like 3 times more. So we will have what, almost 200 milliseconds per one request. But we didn't calculate any routing, like anything like changing the networks, etc. So it will be high no matter what we do. Even if we improve somehow the world infrastructure, it will be too slow. That is why we need this geo-replication. So replicate the data between regions. And the geo-replication, it means that we have multiple data stores, and we would like to make the data between them like the data between them consistent. And the whole difficulty of the geo-replication, it must be asynchronous for the reasons I mentioned before, because it would just take too much, it would be too slow to keep it synchronous. Your data store obviously must support it, which is obviously not something you can take for granted. Geo-replication is not like a feature you have everywhere. And since it's asynchronous, you must be prepared for data loss, which is a big thing when you design a system. And basically there are like two modes in which you can operate. It's active passive and active active. So with the active passive replication, you write only to the one data cluster. And the second one, it can be read only or just non-active. And you asynchronously replicate your data. With such approach, you have to, data loss obviously is possible because you may store something in your active cluster, and before it's asynchronously replicated, the cluster is down. And in that case, you lose some data. And you have to be prepared for eventual consistency. If you choose to use active-active, so you write and read from both of the clusters, that is even worse, because then you have to be prepared for data loss, obviously, for the eventual consistency and for the conflict resolution. Because what happens if you change the same value at the same time in 2 clusters? You need to resolve the conflict. You as an application developer, you have to decide what to do in such a scenario. Like the strategies or the choice of strategies that will depend on your database. Like in Hazelcast, we provide a lot of strategies. You choose which one should be applied for the conflict resolution, and that is in most databases. Some of them, I think Couchbase, they just keep all they keep the tree of all changes, and the user needs to choose which one is the right one. I would say the most common strategy in general for conflict resolution is like first one wins or the last one wins. But obviously you need to be prepared. Your business logic needs to be prepared for that, because that is a big decision what should happen in such a scenario. In Hazelcast, we obviously support geo-replication. We call it WAN replication. And it's very simple to configure. We just specify, okay, Hazelcast WAN replication, and give an IP of the second cluster. If it should be active, then you need to specify the same configuration with the reverse IP in both Hazelcast clusters. So in this scenario, you can have one cluster in London, the second in Paris, and they can obviously asynchronously synchronize the data. You may ask, like, but okay, it's a big, losing consistency is a big thing. Do I really need to lose consistency? What if I really need, like, really want my database to be consistent? And I did another latency experiment. So I've set up Hazelcast on multiple regions, and I make the one consistent cluster in between them. So something that you should not do, but I did it just as an experiment. And the result for this was like that. So while the result for level 2 with the synchronous communication, this was still under 1 millisecond per entry, was good. Here it is super high. So this is not acceptable consistency for any system. And this is why, like, obviously, like for asynchronous replication, it was the same as the level 2. But that is the reason, like, why you really cannot set up your database to be with the strict consistency between regions. That is also the reason why you cannot set up a Kubernetes cluster which works on multiple geo-regions. Because Kubernetes, for the data store, it uses etcd, and it keeps the state consistent with this strict consistency. But if you really need, like, to, I don't know, you work for some banking industry or something, read about like something what is called new SQL. They don't actually solve, they solve some of the use cases of the strong consistency and transactions. But obviously it's always a trade-off between consistency and latency. And this is trade-off that will not be really solved, because it goes to the speed of light. So it's like, we will not do much more. Okay, a short summary. So level 3, multi-region, what does it mean to you? So it means that you are super highly available, and you have low latency if accessed from multiple regions, which is very good. Sometimes possible to use some cloud-specific toolkit like Google Spanner. They mitigate this. But in most scenarios, you will not have, even with the cloud toolkit, like the multi-region. So you need to use geo-replication, which is asynchronous and causes a lot of problems with eventual consistency, conflict resolution, and so on. Okay, let's move on. So next level is multi-cloud. And multi-cloud means that if one cloud provider is down, the system is still available. So this is how our diagram looks like. So there is a global load balancer which forwards the traffic to different cloud providers, and the rest is more or less similar, because we need to have replication between different cloud providers, which is kind of a geo-replication, which we covered in a second before. So our assumptions are, like, machines are in at least 2 cloud providers, network may be slow and unreliable, and machines may be in a different geo regions. So you might ask, like, we do exactly the same as the multi-regional. So what's actually different from multi-regional? So there are some small differences. So the first thing is, if you use multi-cloud, you cannot use any cloud-specific tools because each cloud provider has different cloud portfolio. So you need to use different tooling. You don't have like cloud features like VPC peering across cloud providers. And VPC peering is a good thing because it improves your security and it decreases the latency of the network calls. And now you have to take care of this by yourself. So before you could be, okay, my system is in a one security, one VPC, it's secure, okay? But now you have to take care of the security by yourself. And also the cost, you need to have multiple systems, which means the cost is higher. So is high availability the only reason for multi-cloud? And as you may imagine, no, it's not. It's not even the main reason. The reasons for multi-cloud are usually to avoid vendor lock-in. So you upfront, you design your system in a way that it works on multiple cloud providers because you don't want to be bound to only AWS. It also can help you with the cloud cost optimization because you may take cheaper services from the cloud providers. Also, you may, your position in the cost negotiation is better because like AWS price for a big enterprise is obviously different than AWS price for me. So if you are a big enterprise and you go to AWS to negotiate the price and you say, okay, my system is already working on GCP and Azure, you are in a better position. So also like risk mitigation, low latency, meaning like you can have low latency for the external services which are running in different cloud providers. Data protection, regulation, compliance, as I think is clear. And sometimes you won't like to use specific technology from the given cloud provider, like the Google Spanner. That's why but you like to use Google Spanner, but the rest used on AWS. That's why you mix the cloud providers. So what does it mean to you? There is no vendor lock-in, which is a good thing. You are in a good position with the cloud cost negotiation. Low latency is accessed from multiple, from multiple clouds. That is why, for example, when we built Hazelcast Cloud, with the Hazelcast Cloud, Hazelcast as a service, we built it on top of multiple cloud providers because our users also may deploy on multiple cloud providers. So we would like to provide low latency from any cloud provider. From the downside, the setup is complex and no cloud toolkit can be used because you need to be cloud provider agnostic. Last level is hybrid cloud. So hybrid cloud is slightly different than multi-cloud. If I were to give like a definition of what it is, it means that if all cloud providers are down, your system is still available. But you may say like, but really? I mean, is it possible that all cloud providers are down at the same time? And obviously, no. If all cloud providers are down with all regions, it's an apocalypse. No internet works anymore. So there are different reasons for hybrid cloud. So the main reason I would say is data requirements, regulation, and data security, meaning that there are some regulations that, for example, you are a banking system, and there is some regulation that you cannot store customers' data outside your buildings or outside your country. That is why you build your own data center and your customers' data are stored only there. So, but you don't want to deploy everything on your infrastructure. That is why you create hybrid cloud.
The other reason is like when your infrastructure currently is running on premises, but you would like to move to the cloud. So as a phase of this migration, you create hybrid cloud. Also, cost reduction and everything we already mentioned in the multi-clouds are the reasons. As the diagram, you have a global load balancer, which load balances the traffic to all your system parts deployed on different cloud providers, but also to your system part that is on premises. And obviously, at this point, the setup is so complex, also for multi-cloud actually, that you need some abstraction for your cloud provider, for your servers. You don't want to write a lot of bash scripts and treat each server differently. That is why currently, like, this abstraction is usually a Kubernetes or some derivatives like OpenShift and IBM Cloud. So they are actually OpenShift and Red Hat and IBM. They are investing now in a lot in multi-cloud solutions. So you may have heard a lot about this, and you will hear even more. Because basically you need some abstraction over the servers, because it's just too difficult to work with different cloud providers, with your own machines, etc. That's why you install everywhere Kubernetes and treat every environment the same. Short summary. So hybrid cloud means that you have no cloud lock-in, low latency from access from everywhere, because you can set up your own servers anywhere you want. From the downside, the setup is very complex, and it usually requires some extra layers like Kubernetes, and it costs a fortune. So luckily we covered all availability levels that you can use in your system. So as a short summary, what I propose is to give you a graph how I see it, how I see the complexity of the setup versus complexity and cost versus the high availability level you use. So this will be the diagram. So first, deploying on a single instance is super simple. You have no problem at all. If you deploy if you go to the level 1 multi-instance, then you need to think about, then your system suddenly becomes distributed, which is difficult. And you need to think about data replication. If you go from multi-instance to multi-zone, this is not a big change in terms of complexity, in my opinion. You just need to find the tools that support zone-aware feature. For the multi-region, you have long distance between your data centers, so you need to use geo-replication, which is way more difficult, because suddenly you may lose data, you need to use eventual consistency, you need to think about config resolution, and so on. To move from multi-region to multi-cloud, you cannot use any cloud-specific portfolio tools. And moving to hybrid cloud, it's also a big step, because you need to maintain your own infrastructure, which is another level of difficulty. So now, which high availability level is for me? So I would say, if you don't know, then the best level for you is multi-zone, because it's still pretty simple to set up, and it's very, very reliable. Single instance is if you like risk. Multi-region is if you need to go global with your software. So the business requirement for your software is to be global. Then you will go, it's not for the reason of high availability, but really for the reason of latency from multiple regions. And multi-cloud, hybrid cloud, it's basically for compliance, for banking, to support some requirements, like your data is in your data store, and so on. And with this last slide, I would like to thank you for listening. It was a pleasure speaking to you, and hope we will see it sometime, like live, not only online, but also like in person. Thank you for listening.